Hey guys, in this video we're going to talk about salts. So, we need to know first of all what a salt is. It's not the stuff you put on your french fries. We need to talk about how to figure out if a salt's acidic, basic, or neutral. We need to talk about how to write salts and reactions. And we also need to talk about how to take the pH of salts. So that's what our discussion in this video is going to be about. So, first of all, what is a salt? A salt is any ionic compound. So if we think back to like our very first day in chemistry, an ionic compound is a metal and a nonmetal, or a metal and a polyatomic ion. So you see that I've written three of them here. We have sodium nitrate, that's a metal and a polyatomic ion, so that is classified as an ionic compound or a salt. We have potassium acetate, which is a salt because it's an ionic compound, and we have ammonium chloride. So all three of these labeled here are salts. So we're going to figure out how to take the pH of them by first distinguishing if it's acidic, basic, or neutral. Secondly, by writing what we call a hydrolysis reaction, and then from there we can figure out its pH. We're going to do some example problems, and then you guys are going to do some problems on your own. So when we are figuring out whether a salt is acidic or basic or neutral, we have to look at where it came from. Okay? So where these appear are basically as products for a neutralization reaction. So if you think back to your titration lab that we did the other day, you had acetic acid and you had sodium hydroxide. When both of those reacted, all right, let me write this reaction up here so you guys can get the idea. So when I had acetic acid, HC2H3O2, plus sodium hydroxide, when those reacted, I formed water and I formed sodium acetate, right? So NaC2H3O2. The sodium acetate is the salt one of these salts that we're talking about. So we have to figure out whether or not this is acidic, basic, or neutral, and more specifically, we can take the pH of that. So whenever I have an acid and a base react, you will always form water as one of your products and a conjugate base or a conjugate acid, and that will be in the form of a salt. So another kind of thing to put the big picture together, we're basically looking at our conjugates, our conjugate acid or our conjugate base there. Okay, so we have neutral salts, basic salts, or acidic salts. So the way that I like to distinguish whether or not they're acidic, basic, or neutral is I look for like where it came from in the reaction. Your cations here, so your cation, your cation, your cation, those are the things that are positively charged in your ionic compound. Those will always come from the base, all right? So Na came from NaOH. K came from KOH. And NH4 came from NH4OH. So you notice how what I'm doing is I'm just kind of saying these cations are always coming from the cation OH, the cation OH, the cation OH. That's your first step. Your next step is to distinguish that the anion portion, so these are our anion portions, the negatively charged things in our ionic compound. Those anions, therefore, come from the acid component. So the acid component of this would be HNO3. The acid component of this will be HC2H3O2. And the acid component of this would be HCl. So some people call these like the parents, right? So the parent NaOH base and the parent HNO3 acid come together. They have a little kid that's got a little bit of Na, a little bit of NO3 in it, okay? So these are the parents. This is the kid, the salt. Oh, I have somebody climbing on me. We have a little visitor. A little kitten. I have kittens that I need to get rid of. Sorry for them. And just a little dose of cuteness for you. So we have to figure out what is happening or basically what these parents are. Are they strong bases? Are they strong acids? Are they weak bases? Or are they weak acids? So I'm going to start with this very first salt. And the NaOH, I'm going to evaluate that. So NaOH is a strong base. All right. HNO3 is a strong acid. Now, how I distinguish of whether or not this is acidic, basic, or neutral is by whoever is strong kind of supersedes the other. Let me put this little brat down. There you go. Go to your mom. Whichever one is strong supersedes from the other. All right. So if they're both strong, they kind of like cancel each other out. And so what we have is a neutral salt. Why? Is because it's produced from a strong acid and a strong base reacting with one another. So neutral salts are produced when you have a strong base and a strong acid reacting. Now let's evaluate this second salt here. So we have KOH. That is considered a strong base. If you don't know your strong bases and strong acids by now, you need to know them. HC2H3O2 is a weak acid. So the strong supersedes the other. Since we have a strong base here but a weak acid here, then that classifies this salt as a strong or as a basic salt. This salt is considered basic because it came from a strong base. So we can classify basic salts that they are produced whenever a strong base and a weak acid react with one another. That also classifies as our sodium acetate that we used in lab, right? Sodium came from NaOH. Acetate came from acetic acid. We have a strong base, weak acid, so we had a basic salt. Let me give you something to think about here. When we mix a strong base and a weak acid together, don't our pH increase until we reach the equivalence point, which is in the basic range? Well, why is it changing the equivalence point? Why is the end point in a basic range? Why do we have to choose that indicator that's in the basic range? Mind blown. It's because we have a basic salt that's produced here. So hopefully you guys got that big picture going on there. Okay, so this therefore is a basic salt. Let's look at an acidic salt. So we have NH4OH, that is considered a weak base. HCl, that is considered a strong acid. So strong supersedes because this came from a strong acid but weak base. That makes this an acidic salt. So we can clarify that an acidic salt is produced from a strong acid and a weak base reacting with one another. So that's step one. Being able to recognize a salt and figure out of whether or not it's acidic, basic, or neutral. If it's a basic salt, we're going to have some OHs being produced when it's put in water. If it's an acidic salt, we're going to have some H3O pluses being produced or be floating around in there if we let that salt stay in the water. Okay, so this is what we're going to talk about next. How to write these hydrolysis reactions. Hydrolysis means splitting of water. So hydrolysis, hydro, water, lysis means splitting apart. So we're going to write reactions, and you'll have to do this for free response. You might even have to do this for a multiple choice question. We'll have to write where these salts are reacting in water and they're producing their components there. I'll give you a hint. It's basically a neutralization reaction backwards. Okay? So basically we are starting here and we're going in the opposite direction there. So if we were to write this net ionically, sodium would be a spectator, right? We'll have OH minus, we'll have C2H3O2 minus. So we have hydrolysis going in the opposite direction from the neutralization reaction. This also tells us a basic salt because we have OHs present there. So if I wanted to find the pH, I would have to set up a rice chart, solve for X in my rice chart, which would end up being the OH concentration. And then if I have OH concentration, I can find POH. And if I have POH, I can solve for pH. So that's basically the grand scheme of things of what we'll be doing. So here's the rules. If I want to write a hydrolysis reaction, what you do is you look at your salt. Whatever is strong, I'll give you a little hint, that's always going to be your spectator. So whatever is strong will always be my spectator. So I'm left with C2H3O2 minus. You're always going to have your salt reacting with water. If it's a basic salt, you're going to have OHs present here. And then if OHs are present, then that means so if that's present there, then that means the H has to get with the C2H3O2 minus. Basically, you're making your weak component as your other product. All right, so let me say that again. My salt, I look at it. My strong is my spectator. Okay, my strong side. My strong side's my spectator. C2H3O2 is what's left over then. I react it with water. If it's basic, OHs are going to be my product. If it's acidic, H3O pluses are going to be my product. And then the other product is just the weak component. Notice here, this one is a little different. My weak component would be NH4OH. What naturally happens when you form NH4OH, it actually produces ammonia. And that's just a little extra information right there. You don't have to worry about that. So let's go through some example problems to kind of show you how to do this, and therefore you can do stuff on your own. So let's do exercise 20 on page 19 together so we can get some practice with writing these reactions and going from there. So predict whether the aqueous solution of each of the following salts will be acidic, basic, or neutral. Prove with appropriate equations. So I figure out where each comes from. Let me get my pen so you can see. So Na comes from NaOH. C2H3O2 comes from HC2H3O2. So now I evaluate. NaOH is a strong base. HC2H3O2 is a weak acid. So strong wins, right? Strong wins, strong supersedes the other. Because I have a strong base but a weak acid, then that means that this is a basic salt. So now we have to be able to write that reaction. So we have strong as our spectator. We're left with C2H3O2 minus, C2H3O2 minus. We're going to react that with water, so plus H2O. Since this is a basic salt, we're going to have OH minuses being produced, and whatever's left over is going to come together. And another way you can think about this, thinking of water as HOH. We know that positive and negative things come together, right? Well, H is the cation portion, so the positive H is going to get with the negative here, and therefore I'm left with the OH by itself. So there's lots of different ways that you can think about who's getting with who and all that good stuff. So therefore, H and C2H3O2 is going to come together. HC2H3O2 is going to come together. A way to check yourself is the weak component should be one of our products here. So that's another way you can look at it as well. So this would be our reaction. Now, if I wanted to find the pH of this, I would be given an initial concentration of the salt. I would end up setting up a rice chart, solving for OH, plugging that out. Also, I'd be given a Kb. So if I have a basic salt, I need a Kb value. If I had an acidic salt, then I need a Ka value. And from there, when I find X, which is my OH concentration, I find POH, and then I find my pH from there. And I think I have an example problem that we'll do in just a minute. For this next one here, NH4 comes from NH4OH, which is a weak base. NO3 comes from HNO3, which is a strong acid. So strong acid wins. Therefore, this salt is acidic. We have to write the reaction in order to display that it is in fact acidic. So remember, strong wins. Therefore, it's a spectator. So we're left with NH4 plus H2O. Think of H2O as HOH if you need to. Since this is an acidic salt, I'm going to have H3O pluses floating around here. And what's actually going to happen is I'm forming NH4OH. NH4OH will always break down into NH3. So maybe that's just like a rule that we kind of need to know. Whenever I have NH4OH produced, it will actually break down naturally into NH3. So now let's look at our last one. We have Al, which would come from AlOH3. We have sulfate, which would come from H2SO4. Which one is strong, or are they both? Aluminum hydroxide would be a weak base. Sulfuric acid would be a strong acid. So this is an acidic salt once again. We have our strong, which is our spectator. So what we're left with is aluminum ions plus water. So we are going to write the reaction. H3O pluses are what's produced, plus AlOH3. And what I would have to end up doing here is writing my balanced reaction. I think maybe it's balanced. It might be balanced, it might not be. But you would have to balance it at the very end. So this is how we determine if it's acidic, basic, or neutral, and write the hydrolysis reactions. Now we're going to take it one step further and figure out their pH. Alright, so let's look at this example problem here. We have calculate the pH of 0.3 molar NaF solution. So first of all, what we have to be able to do here is look at NaF and realize that it's a salt. It's an ionic compound, so therefore it's a salt. So from there, we have to figure out if it's acidic, basic, or neutral. So Na comes from NaOH. F comes from HF. NaOH is a strong base. HF is a weak acid. So strong supersedes. So this is therefore a basic salt. The next step that we have to do is write our hydrolysis reaction. So strong is our spectator. So we're left with F minus plus water. That means that OHs are going to be produced, and we are left with HF. Now what we're going to do is figure out the pH by first figuring out what the concentration of OH is. So water is not included. This is very similar to what we did for weak acids and weak bases. F minus is 0.3 molar. 0 for OH, 0 for HF. Minus X plus x plus x. I'm just filling out the rest of my rice chart. So we have 0.3 minus x, x, and x. Now, this is where you have to pay attention. If I have a basic salt, I have to use a Kb value because I have OHs that are present here. Notice what they gave me. They gave me a Ka value. So how do I find a Kb value from a Ka value? This is where we use the Kw formula. Kw equals Ka times Kb. And if you remember, Kw is the equilibrium constant for water. And that number is 1 times 10 to the negative 14. So I'm going to plug in 1 times 10 to the negative 14 here. The Ka value here, 7.2 times 10 to the negative 4. And I'm going to solve for Kb. So I end up finding, I did the math over here myself, I end up finding that Kb is equal to 1.39 times 10 to the negative 11. So this is the K value that I'm going to use in order to help solve for X, which is my OH concentration. So I write my Kb expression. That's equal to OH minus times HF over F minus. Now I can actually plug in numbers. So I'm going to plug in 1.39 times 10 to the negative 11. Then that's equal to x squared over 0.3 minus x. This is also a situation with the 5% rule that AP does, like I've told you with the weak acids and weak bases, where we get to, don't you love that neglect right there? We get to neglect x, okay? So therefore, it makes my math easier. The reason why this little x number is insignificant. So we take 1.39 times 10 to the negative 11 times 0.3 is equal to x squared. We take the square root. So that means x is equal to 2 times 10 to the negative 6. Now it's very important to know what x means. X means the concentration of OH, which is this here, okay? So now, what do? Well, I'm going to have to find a pOH value first. So pOH is negative log of OH concentration, which ends up being 5.69 that I calculated before, 5.69. pH, therefore, is equal to 14 minus that number, which is 8.31. So 8.31 is our answer there. So that is how I take the pH of a salt. Ooh, somebody got mad. If it is an acidic salt, then I write my reaction. That's what exercise 22 is about. I write my reaction, but I'll have H3O pluses here. So I will have to be using a Ka value. And then when I solve for X, that ends up being the H3O plus concentration. So I just directly plug that into my pH formula. So if you need practice with that, with an acidic salt, then exercise 22 is for you. Okay, so I'm going to get out of here. Hopefully when you guys do some practice problems and things like that, then you will be good with pH of salts, and then we can move along. So ta-ta for now.